Hello, and welcome to the second episode of the AwesomeAlgo podcast. And today's guest is Zeph Grunschlag. He is a senior software engineer from Algorand, and he has been working in the industry. And please correct me if I'm wrong. Uh, for more than past 20 years, and he has an incredible academic background about which we're going to spend some time talking in the introduction. But the main topic of the episode is continuation on smart contract testing, and we are going to talk about the project that Zeph is currently working on under Algorand called Graviton, which is a testing toolkit for smart contracts. And as always, I did my due diligence to prepare for the episode by actually digging into the repository, cloning the repo, spending some time and going over the code base, documentation, and examples available. There will be some closing notes later in the episode where Zeph will also kindly talk a little bit about how open source developers and enthusiasts can actually help shape the project and potentially contribute, since it's available publicly on GitHub and under MIT license. And with that, let's proceed with the episode. And first of all, Zeph, huge thank you for being here as a guest. And it's incredible to have another episode also as engineer from Algorand, and especially with your academic background. So perhaps we could kick it off with the first question on your background a little bit. Tell us and our listeners a bit about yourself and how you got into engineering in the first place. And we got plenty of time per each section, so don't feel constrained or rushed to answer any of the questions.
Yeah, thanks, Al. It's really exciting to be on your podcast, and I appreciate all the work you've been doing in your AwesomeAlgo repository to cultivate for other developers resources and I've actually used your AwesomeAlgo site itself, so I'm very excited to be on. So let me tell you a little bit about myself. My academic background in particular, I got a Ph.D. in math, and the road to get there had some interesting twists for sure. I got a bachelor's in math, first of all, at Princeton, and it was a very interesting time at Princeton. Some particular highlights: I learned algebraic number theory from Andrew Wiles. That's the man who solved Fermat's last theorem.
Oh, wow. Yeah. I think I've heard that surname before. And if I may ask, what year was this?
This was 1988 when I took that course from Andrew Wiles. And I remember that he was teaching us about the proof of Fermat's last theorem for the case n equals 3. And this is also before he proved Fermat's last theorem. I don't think he's been doing any teaching of undergrad since that proof got accepted. And he was teaching the case for n equals 3. So Fermat's last theorem is a theorem about every possible n, value of n. So he started off with maybe the second most trivial case, n equals 3. And on 2 consecutive lectures, he got stuck halfway through the proof and called the lecture off. So this is something that hadn't happened to me with any other professor, where he just getting stuck and says, "Okay, sorry, I'll do better next time, and I'll show you the proof." And I also remember seeing him at T after I presented the final take-home exam for algebraic number theory. Oh, and Princeton had this idea. Princeton Math has this thing called T, where basically everyone's invited every 4 p.m. just to hang out and have cookies and tea. And so so he was there, and it was really great thing to have. Well, I was waiting for my results for my final paper, which was 15 pages handwritten, and I was anxiously hoping to get a good grade. And he told me that it was one of the most painful to read solutions that he had ever had to suffer through. And he could not find a mistake, though, so he had to give me an A. So therefore, that kind of taught me, maybe incorrectly, that it's only important to be right. Style doesn't matter, right?
Yeah, I mean, at the end of the day, it's all about the content.
Yes. But later I did understand why he was so terribly unprepared for class and lacking in patience. And this was because he was 5 years into the 7-year stint where he was spending every free moment of the day hunkering in his attic and working on solving Fermat's theorem. So I became a little more forgiving of his approach, given the amazing result that he came up with. And also later, I learned to appreciate that style does matter. Maybe it's technically sufficient to get the code for a smart contract correct, but if you have others that are supposed to understand the code or modify it or gain greater confidence that it's not going to cost you $10 million because of a bug, you better simplify it as much as you can. So I also abandoned that very tedious way of writing math. Other amazing people that I met while at Princeton was John Nash. He's as a Nash equilibrium and in game theory, and also the subject of the movie A Beautiful Mind. So he would come to the afternoon teas. And John Conway, the inventor of the game of life.
Oh, wow.
And the cellular automata, who was probably the most engaging of all the professors when it came to interacting with undergraduates. But he unfortunately passed away into 2020 from COVID. So I just feel very lucky to have experienced all that as a Princeton undergrad in math.
Yeah, that must have been an amazing experience,
Yeah.
meeting people of that caliber. And have you had the chance to also participate in classes under their lectures presented, or?
So Nash was not really teaching, but he was still welcome by the communities and coming in for the tea. And I didn't actually take a class with John Conway, but one of my friends did his undergraduate thesis with him, so I heard a lot of interesting stories that way. So then I pursued a PhD in math at Berkeley, and there I fell in love with topology and decided to work with John Stallings, who was working on the Poincare conjecture, now known as Perelman's theorem. Mm-hmm. And Perelman is the guy that refused the $1 million Millennium Prize for solving it. So I ended up doing my research in that area of combinatorial and geometric group theory. So my thesis included results that related certain families of groups to classes of formal languages and described the computational complexity of those various algorithms. And so it was very computational in nature, and it was possible at that point to think about transitioning to theoretical computer science when I got my PhD, and that's what I decided I wanted to do. And basically that's when I ended up going and becoming a professor of computer science at Columbia University.
Yeah. That's quite interesting. So you actually had direct decision-making in your career in regards to switching to the computer science by the end of the pursuing of your PhD. Would you say you also had some significant influence back during the Princeton years, or what was the main decision-making factor to switch from the math specifically to the computer science area?
Well, it's been a love-hate relationship that I've had with computer science. I would say no, I'm definitely in love forever. I'm not going to abandon it. But I remember taking this class at Princeton where I learned C and spending hours and hours getting stuck because I didn't put a semicolon somewhere that I need to put in. and I did quite well in that class, but I was I thought, this is ridiculous. I can't live my life spending hours trying to figure out where semicolons are.
And was it your first programming language, by the way?
It was not my first programming language, but it was the first time I think I was doing something very serious. Like we were actually we were programming on a Iris computer, Silicon Graphics Iris computer, that lets you represent three-dimensional models in real time and depict them. And so it was a pretty advanced code and lots of pointers. And I didn't understand that, yes, you can learn how to debug very well and become much better than not spend 90% of your time debugging, but more like maybe 10%. With modern IDEs like VS Code, maybe only 5%, where you're just staring and like having no clue what the hell's going on. But at the time, I was like, okay, I need to find something purer than this computer science thing, and math seemed like a better approach. But then I tempered with that, and by the end of grad school, I was like, well, I took some courses in C and C++ and Java while at grad school, and my results were computational in nature, and so it seemed like a good idea to get back into computer science at that point.
Interesting. And maybe, sorry, just to backtrack a bit for the listeners out there, in terms of timeline, so we mentioned the Princeton and the bachelor's in math, then you did the PhD. In what year was the end of your pursuit for the PhD degree, essentially? Because there is also a certain period of time that we could just quickly cover for your experience in the industry before joining Algorand. And I suppose the final question would be if you could tell us and our listeners a little bit about your journey into Algorand. So if we could just slowly lead towards that, that would be awesome.
Well, yeah, maybe I also just mention a little bit about why I was so turned on into computer science again in graduate school, and why I wanted to end up at a place like Columbia, teaching computer science versus teaching math. And that was when I ran into the Turing's halting problem, and it really blew me away. And it's also the same idea of Turing's halting problem, I think, is very related to Algorand. And I'll get back to that in a bit, but just keep that in mind. So the halting problem is a very simple question. The question is, will this computer program stop running? But such a simple question, it turns out to be impossible to answer using a computer. And the impossibility proof that uses Turing machine is elegant and simple. So that just caught me, and at that point I caught the computer science bug, and it didn't let go of me. And to answer that question in such a fundamental way, to say no computer can solve this problem, you have to basically get into this very foundational idea of what is computable and what is not, or universal computation. So this notion of universal computation is that what you can do in a program written on the TRS-80 in BASIC, and that was the first programs I wrote were in BASIC on a TRS-80, or in Golang on a MacBook Pro, or using a pencil and paper, lots of paper, or your brain. All of these sorts of problems that can be solved are the same. That is, you can translate that problem across domains, and if you can solve them in one of the domains, you can solve them in any other. So the algorithms we solve by pure thought are exactly the ones that we can write computer programs for. And there are very simple problems that humans cannot solve and computers cannot solve either. So this is a beautiful combination of humility and immortality. So we're immortal in having grasped this fundamental truth about what is the most powerful mind that you can have. And at the same time, we understand that our maximally powerful mind cannot solve some very simple to ask questions. And so that really, blew me away. And I really wanted to do my work in computer science after that.
Yeah, I must say that in general, like complexity and computability theory are just, in my opinion, I also got really fascinated by it during my master's degree, and I would say, like, even if comparing it with algorithms and data structures, I think this is one of those subjects that should be foundational knowledge for many computer scientists out there, because it just covers a very vast area in terms of computability. And maybe another mind-blowing fact is that Alan Turing proved it in 1936, right? This is even before there was any compute possible to also practically prove it. And another fascinating factor is, the fact that it was essentially proven way before people were able to sit here like us and talk over web platforms to record podcasts.
Right, but even with his very theoretical understanding of computers, he was very practically minded as well. He helped, he helped in the effort to decode the German cryptography.
Yeah.
And some say that if he wasn't...
Enigma machine.
Yeah, exactly. And if he hadn't been involved, or people like him hadn't been involved and had their successes, that World War II itself might have gone on another year or two. So literally, his work was very practical as well, saving millions of lives. Really an incredible story. So I got my PhD in 1999, and then I went to Columbia after that as a assistant professor focusing on undergraduate education. After that, I did work in industry as well on Wall Street, and also did teaching at undergrad, at high school and middle school levels. I've had a very interesting career, going and doing lots of different things, including then being a data scientist for my most recent job before Algorand. I just definitely like to dabble in lots of things, but computer science is definitely the most exciting thing in my heart. And so how did I get to Algorand? I first learned about Sylvia Macaulay's work in zero-knowledge proofs while teaching graduate cryptography at Columbia. And this concept of zero-knowledge proofs, I put there in the same league as that foundational work we just talked about by Turing and his cohorts. That was 50 years earlier, before zero-knowledge proofs. So the idea that you can prove that you know something without revealing the actual information is kind of like the symmetric opposite of the idea that you can prove that you cannot know something.
Yeah, it's kind of like going back to what you mentioned was I think I understand it now, is the halting problem.
Yeah, so it's like, and so it's not surprising, given that how foundational is that Sylvia Macaulay and Shafi Goldwasser together, they got the Turing Award for that work. And then, I just knew about that, and I thought, wow, this is really an amazing theorem and amazing work of zero-knowledge proofs. But then I didn't think much about it. But then during COVID, I found myself going in new directions. And that's when I started doing a deep dive into blockchain tech and listened to various podcasts, heard about Sylvia Macaulay's work in blockchain and Algorand. And I was like, oh, wait, Sylvia Macaulay. I know that guy. He's working on the blockchain. Oh, very interesting. So then I dove deeply in there and tried to understand what is special about Algorand. And the more I learned, the more I was impressed by the elegant design principles at the heart of Algorand. In particular, the original design has this very clever sortition algorithm whose only starting point is a verifiable random function. And this notion of verifiable random functions and construction comes directly out of original work by Mikaeli and other colleagues. And in the Algorand blockchain, it gives rise to some very important properties. You can get immediate settlement and finality during consensus. You have lack of forking, and you have this ability to have this so-called pure proof of stake, where you cannot know until it happens who will propose the next block. So you cannot hope to corrupt the process unless you own or control close to the majority of the stake. So I was like, wow, this is a really well-designed blockchain. So if I'm going to work in blockchain, where should I go? Like, it sort of became like pretty obvious. Algorand's the place. And it also gave me the confidence that Algorand is a company that focuses on getting the math, the cryptography, and the software engineering right. And definitely I've seen that in action since I joined. For example, we don't just rest on our laurels. We have, for example, this state proofs coming on board soon. And that's going to allow us to bridge other chains in a more trustless and sound manner than what is the most popular current way of bridging. And we're also, even in state proofs itself, we're forging ahead with quantum-resistant cryptography. And I'm confident that we'll transition to being 100% quantum-resistant long before it becomes practically tenable to use quantum cryptanalysis to crack blockchains.
And just to reiterate on that, we briefly touched this in episode 1 with Cosimo, but yeah, I'd just like to emphasize the fact that I really like the approach that Algorand takes in regards to competition in the space and this realization that the future is multi-chain. There, of course, won't be billions of chains out there in the future, but there is going to be a subset that will prove the use cases and the value and are going to outlast the others. And it's all about allowing them to communicate with each other, because that is the foundation for the infrastructure that is being built.
Yeah, exactly. So it's really been. I mean, I feel like it's just this is definitely the best job I've ever had. You know, it's really great to be part of Algorand.
Well, Zeph, thanks for the amazing introduction. I'm sure there will be a few points in the upcoming sections where I might have to refer back to the information we provided so far. But going further, with you joining Algorand, essentially, I already mentioned that the goal for this chapter, for this episode, is essentially to talk about Graviton. But before we are able to dive into Graviton, let's kickstart a little conversation on the definition of TEAL itself, because I feel like it's an important prerequisite and to define it properly so that the listeners will essentially have all the necessary information to easily follow the conversation. And no, for the listeners out there, we are not talking about colors here. When I say TEAL, it stands for a transaction execution and approval language, which is a assembly-like Turing-complete language that is processed by the Algorand virtual machine. So once again, Zeph, stage is yours. If we could just quickly cover on the TEAL and the definition of it.
Well, first of all, I beg to differ. Teal is a color, and it turns out it's Brian Olson's favorite color. And Brian Olson was the first, basically the inventor of teal.
The inventor of the teal, yeah.
Yeah.
Oh wow, that's an interesting detail.
Yeah. But of course, it doesn't officially stand for that color. It stands for Transaction Execution and Approval Language. And you can think I sometimes pronounce it as TEAL, because TEAL as an Algorand, but that's definitely just me mispronunciating it. So TEAL is the assembly language syntax that specifies programs executed by the Algorand virtual machine, also reference called AVM. And the original name, it is Transaction Execution Approval Language, makes most sense when you think about its original purpose. So the very first smart contracts that existed in the Algorand blockchain were logic signatures. So they were stateless. In that setting, all that a program can really do is say yes or no. You can either approve or reject a transaction. It has no state. You can't. There's no other artifact that's going to outlive it. So then it makes sense to think of it as an approval language. So what TEAL really is comprised of a set of opcodes that are acting inside of the AVM's computational model. And so you might have opcodes that, we have, for example, a stack, and you have maybe an opcode that says push this data to the stack, push, and you have a pop, just like you have in a regular stack. But you have other things as well. So you have temporary memory. The temporary memory consists of the stack, which is has a length up to 1,000, and each element on the stack is either a uint64 or a bytes array, so it's capped by about 4K. So you can't have more than, every stack element has at most 4K bytes. And you have 256 scratch slots, which you can think of them sort of like as registers. So basically you can, as you compute, you could say, I have this value for X, maybe it was 3, and now I squared it on the stack, it's 9, the top of the stack is 9, and I'm going to save that for later in scratch slot number 13. So now scratch slot number 13 has the value 9. But we also have a permanent memory. That's for apps, not for logic sigs. That's the stateful contracts. We have local state, global state, and we have a new type of permanent memory under research called boxes. So I'll talk a little bit about all three of those. So the local state, every account that opts into an app might have some local state, which might let you, for example, if you're opting into an auction app, for example, you want to keep track of what you bid. And things like that. So that would be stored locally at the account level. And the local state consists of up to 16 variables, and these can be either uint64 or bytes of length up to 128. So you don't. It's not, the bytes themselves aren't as big as can be on the stack, but it's enough to do kind of more deeper type of floating point, higher precision floating point calculations. So you can have 128 bits instead of 64 bits. And the global state, so that's the creator, the account that creates the app can also allocate global state. So that state that every person that opts in, every account that opts in can see, but is just kind of global. And there you have a little more. You have 64 of those global state variables, and they're also the same kind, which is either uint64 or bytes of length up to 128. And let me also mention boxes. So again, this is still in research, but I think I'm very confident that we will have boxes in sometime this year. And boxes are unlimited in number. So every app could have an unlimited number of boxes, but with all these things, there's always a minimum balance requirement. So if you want more local state, then account that opts in to the app has to have more mint balance to kind of set that aside. And global state is similar as well, and boxes as well. So maybe you end up being able to have 1 million boxes for some ridiculously crazy app, but in that case, there would be a significant amount of algos that would have to be in that app's account to set those aside. And additionally, we have the execution model, which is based on opcodes, every opcode has an associated cost. So that's kind of like in the Ethereum world, there is this notion of gas. There is no gas in Algorand smart contract development, but we have opcodes, cost. And most of the opcodes have a cost of just one, but some of the more intense opcodes like basic cryptographic signatures, things like that, can have much heavier cost of computation. Therefore, the opcode cost is significantly higher. So logic SIGs allow you up to 20,000 of total costs for every computation. But apps, that is stateful apps, only allow you 700 total cost. Mm-hmm. However, we allow you to decide. There's a notion of opping up. That is, if an app has an inner app call inside of it, you can pool the budget, the opcode cost budget. So if you have one inner app, instead of just having 700 total costs, you can have 1,400, two times 700. And you can keep on pooling. If you have a very, very complex type application, you can have up to 255 inner app calls. So for a total of 256 apps, all inside of one call, and that gives you up to almost 179,000 cost budget altogether where you max out. So that's kind of our way of letting you have more complicated code without having to kind of put those in a group transaction or something. I can do it all in one app call.
And just to backtrack a little bit on the definition of the opcode, because I'm sure many listeners are familiar with the definition from computing, that it's a portion of machine language that specifies the operation to be performed. But what's Algorand take on the definition of opcode?
I'm not sure if I have ready in my mind like the official Algorand definition, but I would think of it as I work with the actual code, and an opcode maps to a function in Go. Right? We implement our AVM in Golang, and so there is actually, you could look at our open source and you'll see that every opcode there is actual function in Golang, and it'll do it's not actually assembly, it's actually doing stuff in Go. So we try to be, that's why we have a lot of maybe that's why we used Uint64 from the very beginning. That's kind of a Go native type integer, unsigned integer. So yeah, so at the end of the day, that's I think of an opcode as just some Go functionality.
Interesting. Yeah, I mean it's just that we're building up all the prerequisites to Graviton. So just wanted to give a little.
I should say there are some specifications for all. We have the Algorand Foundation owns the specs, and before we have to kind of work with the Algorand Foundation to make sure that opcodes make sense and are approved, and they are defined in some formal sense. Like, this is what the opcode is supposed to do. It's not just like, look at the code. It's it's just the code is supposed to adhere. But often, like, there's like the user community say, well, we really need this such and such opcode, and we might, as developers, try to experiment and let's say, hey, that sounds like a good idea. We have a reference implementation for it, and then we might, there's a back and forth with the foundation, It's not always, they're very open to new ideas, and wherever they come, whatever the good ideas are, wherever they come from. So it's not like we're just listening, for the foundation to tell us, we need this opcode, do it. Sometimes that happens too, but yeah.
I see. Yeah, I'm sure the listeners out there also could recall some mentions and references we made in the episode 1 with Cosimo as well. There is a collection of the documents called ARCs, which is Algorand's take on the RFC documents, and you could essentially inspect them. They're all available on GitHub, and you could essentially dive into any specification you might be interested in. So,
exactly.
Going back on the topic of TEAL, in contrast with languages, other popular languages, or for other blockchains out there, such as Solidity, or if we are looking at general purpose languages, is there any specific and I would say concise reason that you could say that was behind TEAL, being designed as this assembly-like language, essentially, in contrast with other tool? Because I suppose, of course, there's a huge benefit in terms of computation and performance, but I suppose the other aspect is the appeal towards the general Web3 space and the engineers out there who are trying their hands on this, and assembly-like languages in this day and age don't feel like something that is that have a quick learning curve in some sense.
Yeah, I definitely appreciate that. Though I think, given my history having taught computability, I always loved Turing machines as they were. So like, wow, this is really cool. I really love the idea that you can write smart contracts in very Turing-like language. But actually, I don't think there is really that big of a dichotomy between Algorand and TEAL and the world of the bigger world of like Ethereum type, Solidity type programming, and I think it's really a question of emphasis. So from a smart contract philosophy point of view, there's really more that Algorand and Ethereum landscape have in common that makes them different. I mean, really, Ethereum has the EVM, the Ethereum virtual machine, and that's the analog of our AVM. But the Ethereum Foundation did put forward a Solidity pretty early on as a recommended language to compile into EVM bytecode. There's other ways you can do it too, like Viper, from my understanding, that compile to their bytecode. And similarly, we have PyTeal, which is kind of like Solidity. And there are other ways to generate TEAL from a higher level language perspective, like Reach. And I'm pretty sure and there's other ways as well, like third-party approaches. And I think that ecosystem is just going to grow. But if you look at our history, early on, it's true, there was no higher level language, so you had to write in TEAL, and that made a lot of sense early on. It wasn't that big an issue because we were only supporting stateless logic SIGs. And intentionally, TEAL was not even Turing complete at the time. So it wasn't very powerful. And therefore, the advantage of using a high-level language wasn't as big. Like, for example, you want to be able to write a for loop. Well, you couldn't write a for loop in the very first version of TEAL. That would be impossible because you couldn't have a back jump. And so, it made sense. Like, I think that's part of the philosophy here. Just address the problem at hand and don't, see how things evolve. And yeah, I think I don't know if, I don't know for sure that we knew that we were going to end up going to a more Turing complete model. But I bet you that was the sense. But even with that being the sense, you're like, well, this is the problem at hand. Let's not, put the cart in front of the horse. So we just there's no reason to kind of start.
I see. Yeah, I mean, this is just something that for, certain group of engineers to certain domains may have seemed like a misconception back in the early days. And like the reason I brought this up is essentially to put this emphasis on the fact that the ecosystem is not stale. It keeps expanding. There's higher level languages and solutions being built for that. So I think TEAL should like the fact that for some people it may seem like it's an assembly like language shouldn't be off-putting, because there are just so many ways these days that abstract away that layer and allow you to transpile it from different languages, and from languages that are essentially convenient for yourself. And the learning curve will only get better as the ecosystem is growing in some sense.
Yeah, I think also if you looked at the original Ethereum history, back in 2014, there wasn't Solidity, I believe, and then you would have had to write EVM bytecode, I would think. So no one remembers that anymore, because it's like that maybe you had such a small number of people that cared about it at that point. And now, like, so if you compare the number of people developers that care about developing for Algorand now compared to the time early on in Ethereum's history, it's probably a lot bigger. So maybe but it's more of an issue. And so people, it seems a little odd that we have this TEAL, but I don't think, I think really it seems like most people, more and more people are developing either in PyTEAL or Reach. So I don't think it's as a big an issue. Yeah.
Going further to finally make a segue into testing, what would you say are the most challenging aspects of testing smart contracts written in TEAL?
Yeah, so my own challenges and what motivated me to come up with Graviton is I wanted a super quick way to use test-driven development when developing in PyTEAL. So for those listeners not familiar with test-driven development is the idea that before you actually write the code that you're interested in writing, you write a test for the code. And of course, the test will fail because there's no code backing it. And then you write the code and get the original test to pass. And that's how I like to develop whenever possible. But I wouldn't be able to do the same thing in PyTEAL. And so, for example, suppose I want to write a subroutine for the cube root of a number. I should be able to write a unit test that, just as I would in regular Python, that asserts that the cube root of 8 is equal to 2. And that the cube root of 9 errors because it's not integers. Suppose it's a cube root that only deals with integers. And then I should be able to write a PyTEAL subroutine that computes the cube root and run that unit test against it and see immediately if that PyTEAL subroutine works or doesn't. But, so that was like the main challenge for me. I think that's in a pretty good spot. I feel like I could do something like that now with Graviton and PyTEAL. But there are many other challenges. I'm not a typical Algorand developer. I'm a core developer, and end users have different needs. So our product team actually has researched this very question, like what is the biggest challenge in testing? And often developers submit an app call transactions, and either it succeeds or it fails. And if it fails, all you know is that it failed, and you don't know why. So that can be very frustrating. And it's even more pronounced if you're authoring in PyTEAL, for example, because there's an extra layer of indirection. Maybe you did get some kind of opcode related error or something like that, but it's not going to help. But then you're working in PyTEAL, you don't even realize there's an opcode. Now you should. I think I strongly encourage anybody developing in PyTEAL to understand the opcodes that are being used because you want to understand the costs involved and so on. But that's a separate question. Now, another problem that people have pointed out is coverage in a formal sense. Like, I think this is not just a problem for Algorand. I think this is just a generally difficult problem across all blockchains. But the solidity space is more developed, not surprising, it's been around for much longer. So they do have, I think, more ways of addressing this. But there ought to be a way of enumerating all the possible relevant inputs that inform a smart contract and test against these. So there's one way would be formal verification. So you analyze the code and input domain and give a formal specification for that. Now, I know there's a company called Runtime Verification that has been used for various Algorand smart contracts. I don't know much about their specifics, but that would be nice, for example, if there's also an open source version of that.
They do the audit reviews for the smart contracts, right?
They do a lot of reviews, yes, for smart contracts. They use formal methods, from my understanding. Then there's another thing that would be great for understanding testing across important inputs. That's the technique of fuzzing. And that's where a program's compilation helps guide automatic test case generation using genetic algorithms. So that's actually fuzzing is now part of core Golang. Like Golang actually lets you very easily do fuzz testing.
Interesting.
So that would be a very nice thing to be able to do, say, for TEAL programs. But I think that's also a very hard problem. And then the last thing in this nature of basically being able to enumerate all possible relevant inputs this is a little bit more at hand. It's called property-based testing. So in Python, there is the hypothesis library that does property-based testing. So there, you don't necessarily have to understand the compilation of a program, but you still generate very wise inputs. For example, maybe like if your input, you look at all integers, all positive integers, well, this wise property-based test will test the case n equals 0, because that's the edge case, like boundary conditions and things like that. So I think the property-based testing would be a very useful addition. And that's, I think, within reach, even within Graviton. It doesn't exist yet so much, but I could imagine a future version of Graviton being smarter about looking at the domain and maybe leveraging already existing libraries in Python like Hypothesis to generate very smart test cases.
That's very interesting to hear that one of these inspirations is this Python library, which I had some brief exposure to as well. I actually use it for one of the Algorand projects that I maintain open source. And it's for listeners out there, if you have a Python code base and if you want a solid setup for unit testing, but at the same time you're pretty lazy to generate the test cases, but you want a very extensive coverage and catch various interesting edge cases. I think I definitely check out Hypothesis. It's a very powerful framework for testing. And to expand a little bit on this, so we are already touching on some of the motivation points for the creation of the Graviton. And one particular thing I just also briefly wanted to touch before we dive completely into it, I'm pretty sure most of our listeners coming from the engineer's background, they realize the importance and the vastness of terminologies and practices when it comes to testing and software development. And you mentioned the TDD methodology, which often these days, I suppose, also goes with the behavioral driven development, which is also a nice methodology for software development, I would say. But one particular thing that I found interesting from the Graviton documentation is this notion of the black box testing. And if I understand it correctly, black box testing is a term that is abstract enough to be applicable to various layers of testing, starting from unit tests, then integration components, testing, contract testing, and etc. Could you expand a little bit on your take on the black box testing and the importance of it in Graviton, essentially?
Yeah, so for me, black box testing connotes two different kinds of black boxes. There is maybe a more traditional sense in software development that is a box that is black, which is the opposite of transparent. That is, you only care about the inputs and outputs. But also there is the black box that an airliner, commercial airliners use to help with post-mortems. Mm-hmm. So the first kind is viewing the code as a black box. So you can imagine you have a flow diagram and you have your function that you're testing. You think of it as a black box. The inputs are going in and you just observe the outputs. You don't know what's happening inside the black box. And you're just asserting that the outputs are exactly what you think they should be. And for Algorand, this kind of strict sense black box testing can be done with standard execution on the private or test network. It doesn't require the so-called dry run capability, because we're only curious about the inputs and the outputs. We don't need to dig deeper into what exactly happened during the execution. But I think the second kind of black box is even more informative, and that can be done with dry run. So the second kind, again, is that the black box that is on every passenger airline and every passenger airline is supposed to carry in its cockpit. And this black box is an almost indestructible piece of tech which can be recovered after the crash and records important bits of information like the elevation, the speed, the angle of the plane, the final minutes before the crash. And in Graviton, the analog to elevation, speed, angle of the plane, and so on are things like the stack trace of the run during the entire run, the evolution of the scratch slots, the logs that resulted, and so on. And this sort of information can be provided, and you can answer questions like, what was the top of the stack at the end of the execution? What was the final log? Which is very important now with our ABI methods, which I can talk about a bit as well. But now when you think of smart contracts as method calls with outputs, those are logs. And so the final log is very important. Mm-hmm. You can also ask things like, what was the maximum height of the stack? Maybe we're getting close to the 1,000 height limit or something like that. What was the final state of the scratch variables? What were error messages that occurred? What was the cost of executing? And also, the basic thing you need to be able to answer is like, did this execution pass or reject? Mm-hmm. Yeah.
I see. Yeah, I didn't realize the extent to which there are some analogies that are being taken from the definition of the black box testing, and I think it's certainly a great way to also count towards some of the motivation, I suppose, behind the creation of the framework. But going back to Graviton, essentially, so I think it's certainly time for us to finally dive a bit deeper into it. Perhaps as an entry-level question, you could just briefly describe why and how did the name come to be, and I suppose you got inspired by some theories from quantum gravity. If you could just briefly tell to our listeners how was the inspiration for the name for this library, essentially.
Yeah, so there was various ideas for names, all physics related, like Higgs. Like as the Higgs boson, that got nixed. People didn't like that. But so the basic idea, the graviton is a particle that hasn't been proven to exist yet. I think most physicists that work in gravity probably believe it exists, but it's never been truly discovered. And that I like that idea. It reminded me of smart contracts in general, because smart contracts, you want to be able to prove there's something, be able to prove that it's totally correct, right? There's nothing possibly wrong.
There's no human error, there's no human factor in there.
But typically, I think it's almost impossible to do that. Yeah, maybe there are some formal verification techniques, but even with a formal verification technique, maybe there's a bug in the fundamental implementation of it. Like it turns out that the AVM is making a mistake somewhere. God forbid, but that could happen. And so you want to be able to kind of find the needle in the haystack that proves that the thing is correct. Just like you need enough experimental evidence to prove that a graviton exists. So it's not exactly the same analogy, but I like the idea that we need to be totally confident. We need to run experiments. It's not good enough just to write the code and think it's correct. You need to be able to test it. And you want to do as much testing as quickly as possible and easily as possible. So because of that, that's why I like Graviton.
I see. So to continue on the Graviton, essentially, just to backtrack a bit for the listeners, Graviton is a software toolkit for black box testing of smart contracts written in TEAL. And I think it's finally time to cover some of the key features of the package. We now have some information on the motivation behind the creation of the framework, and this was a take on essentially enabling test-driven development for TEAL smart contracts in the Algorand ecosystem. But if you could just expand a bit, Zeph, on the overview of the key features of Graviton, and in your opinion, what makes it special?
Yeah. So as far as I know, what makes it special, as far as I know, and there are no other public repos in the Algorand ecosystem that get this exact same functionality, is I guess the first thing is the ability to call TEAL programs or ABI methods or PyTEAL subroutines and immediately make assertions about the outcome of those executions in Python. So it's going back to the test-driven development approach. So for example, if you have an ABI method that takes a dynamic string array and supposedly concatenates those strings and takes the SHA-512-256 hash of them, you can simply supply that array as a Python list to Graviton, call the dry run executor object on it, and assert that the run's last log is equal to the Python computation of that hash. And you can do it very, without any other machinery inside of Graviton. So this is the PyTEAL version of it, but everything if you look at the PyTEAL repo, it uses Graviton and expands on it, and to make it easy to use with PyTEAL as well. And so Graviton figures out how to set up the dry run for you and convert the inputs to what the dry run expects, and then knows how to decode the types back into Python. In this case, to bytes object of length 256 for this hash example. And so you just write the tests in Python. You just say, well, I know how to compute this in Python. This is how you do for the SHA-512-256. Let's have this PyTEAL code run this subroutine. And did I get the same thing? And so that's kind of the number one thing that it can do. So-called, I call this Python assertions, being able to make assertions in Python. The next idea that's kind of related to that are so-called program invariants. So this is the ability to assert that invariants hold about particular TEAL programs, ABI methods, PyTEAL subroutines on a set of inputs. So for example, if you look at the PyTEAL repo, there is a subroutine that computes the greatest common divisor of two numbers using the recursive Euclidean algorithm. So, we have the greatest common divisor, like the greatest. It's the number, the biggest number that divides two numbers that are given. So, for example, the greatest divisor of 10 and 15 is 5. Because 5 divides 10 and 5 divides 15. 1 is also a divisor, but it's not the greatest common divisor. So the last log in this case, so the way you write this invariant, the invariant is that when you take this TEAL GCD computation and you take its last log, the results, it should be the same as Python math library's GCD. That's all it is. You just say, like, though we assert that those two things are equal. Or maybe you assert more things. You assert that you think that your PyTeal program should store it right before it logs out, but it stores it in scratch slot 0. So you can assert, scratch slot 0 is also going to, in the Python world, be equal to the base, the greatest common divisor, the two numbers. You can also make this, it turns out that that's the top of the stack. You also want it to be at the end of the execution, have that value, so you know that the program is working the way you think it is. And maybe you also want to know that you don't take up too much stack. Your stack height never gets too high, so you can give bounds that are also part of the invariant. And also you want to have an invariant that no errors are encountered, and so on. And then you can state those invariants and then run them against 20 random pairs of numbers less than 1,000, say, and just kind of declaratively declare what invariants should hold, and then automatically run a test asserting that. But you do have to provide the inputs by hand. That's where it's a natural dovetail. A future version I could see using hypothesis.
Yeah, this process will be simplified.
So even that part can go. So even that part can be automated. And the third thing I want to be able to do, that I think it helps it stand apart, is the so-called Exploratory Dry Run Analysis, or EDRA. And this is basically a spin on EDA, Exploratory Data Analysis. So that's
this is coming from your experience as a data scientist previously.
Exactly. Yeah. So in data science, we have basically when you first say you're coming up with a machine learning model, the first thing you want to do is you want to understand what is the data that's being modeled. Like, So you typically you put it all inside of a spreadsheet, and you have lots of rows, and you look at what are the columns that. Oh, we have a column for salary, and so that's numeric. Then we might have, suppose I don't know, like you're trying to predict salary based on which college somebody went to or something like that. And so maybe then you have a column for college, undergraduate, and then but that's a discrete. So you have to understand that there's a set of 10,000 possibilities for the second column, but infinite many possibilities for the first column. And then you might want to know, what does it mean? And what is the median? And so on and so forth. And is there any missing data that's not in this data set before I start writing a complicated ML model to try to simulate it or to predict it? So similarly, before I even know how to do like this example of program invariants, I want to know what are the program invariants. Well, how do I know what the program invariants are? Some of them, obviously, I wanted to compute the thing I wanted to compute. But what if I want to be able to assert something about the size of the stack, maximum size of the stack? Well, I want an easy way to just dry run the subroutine, the PyTeal subroutine or whatever, the TEAL snippet, and again to lots and lots of inputs, and just give me a spreadsheet shows me all the possible variables. I can take mean on them. I can do other things. I can even draw graphs in Jupyter Notebook based on them. So in the PyTeal repo, if you look at the Euclidean algorithm example, it continues and it generates a comma separated values, a CSV file with run row for each of the dry runs. And you can quickly eyeball and see what the final opcode cost
Final
was.
message,
final message, the value of the scratch variables, the top of the stack, and so on. And this can be, and in the Graviton repo, there is a Jupyter notebook with a logic sig that's supposed to send an amount varying from 0 to 10 algos, depending on how close the logic sig arguments were to a solution of an algebra question. And basically, so inside of a Jupyter notebook, you load those dry runs results, you collect them into a data frame, and then you can graphically analyze the behavior of the logic sig on a 3D graph, and just see, it does. See, understand. Like if you saw that all of a sudden it goes up in a place you didn't expect, there's something wrong with this. I thought this could be useful in certain cases as well.
I see. Yeah, I would say the key features are certainly impressive. I can see a lot of potential in there, especially as the project continues evolving and the user experience in regards to easily integrating it into existing projects. As this aspect is improved over time as well, I believe there's great potential in Graviton becoming a go-to solution especially for projects who rely on pure PyTest and PyTeal for development of their smart contracts. But I'm sure there will be perhaps other clients for other languages. I'm just a bit curious as well on what was the reason behind using Python as because if I understand it correctly, the majority of the implementation is done in Python for Graviton, right? And given your mentions of the Golang, for example, perhaps you could just briefly expand on the reasoning behind specifically choosing Python. Was it somehow influenced by the fact that there was a need for some advanced integration testing in PyTeal?
Because the original genesis of this was wanting to be able to test PyTeal, and so it made sense for the test to be run under PyTest framework and be able to understand Python basically. Though there are some limits, right? I think if I had to choose another language, that can do other things that are better for us for testing would be Go itself. Go, because for example, the fuzz testing capability, I think it's going to be nearly impossible to do the fuzz testing in Python. But it's a tool. It's probably not going to be the tool for every possible kind of testing, but it's very helpful, especially in PyTeal. And if you're in PyTeal, you're kind of stuck. You should use Python.
Yeah, I see. For the listeners out there, I'm sure the overview of the key features of the Graviton is something that might spark a lot of interest from the ecosystem, especially from people listening to this podcast. Any chance you could perhaps mention on what would be the easiest way to get started and eventually contribute to the repository if there are some open source contributors out there interested in? And just to reiterate on the fact, Graviton is under active development at the moment, and there is you could actually, by just subscribing to the repository, you could see the evolution development process in real time, essentially, which is a pretty interesting aspect to have an opportunity to look into the development process of Graviton, which, as you can hear by the description from Zeph, is in the longer term is going to provide a lot of power in regards to testing of smart contracts in TEAL.
Yes, in terms of community contribution, what is a good way to do that? Is that your question?
Yeah, like let's say there is some person who finished listening to this episode and he is just really eager to try on Graviton. What would be the easiest, or what would be your advice for a great starting point just to get familiar with it?
Yeah, so there's a couple of ways. I think the easiest way is to look at our issues. So there are issues that are labeled with community welcome tag, and those are very, I think, low-hanging fruits that you could get started and help us out. So we would like some improvements in our CI/CD process. And a big one that would be an easy win is being able to pip install Graviton. Right now we can't pip install it. So we'd love to start publishing a repo to PyPy. And I think, but please don't limit yourself to just those. But if you have a clear no-brainer bug fix, you could just open a PR, like a 2-3 line improvement. I think that's going to be welcome without any questions. There'll be some questions, but you should feel like you can always open a PR to have a bug fix. But if it's something less immediate or it's a more complicated bug, then I recommend creating an issue first and start discussing. But always feel free to. I have I think my email is open. Yeah, I'm not sure about that. Yeah, you can email me, but I'm not sure how obvious it is what my email is.
I think there might be an email attached to your commits that you make on GitHub, right?
Okay, yeah. So I'll probably see that on GitHub. Yeah.
So the most committed open source contributors, I'm sure they'll find a way to reach out to Zeph. And to recap on the section on Graviton that we just had, so we had the discussion on some of the prerequisites required to understand the topic. We covered the motivation behind the creation of the framework. We had a overview of the key features of Graviton, what makes it special, and Zeph was kind enough to essentially go over all the types and provide an overview of different types of assertions that are available in Graviton. Perhaps as a closing note for Graviton specifically, is it possible for you to provide just a brief glimpse into the future, developer roadmap? What's the future for Graviton looks like, essentially?
Well, I think we have the ABI coming on board, and I didn't talk much about the ABI, but that stands for Application Binary Interface, which is a way to interact officially through the ARC4 specification with Algorand smart contracts. And we've gone part of the way to exposing that, but I think there's a lot more improvements that can be done. So I think unifying the way we test dry runs using this new atomic transaction composer would be a big win. I think what I mentioned before, the hypothesis-like testing, the property pit testing would be a big win. And as dry run itself hopefully improves in the future, I think there's a lot of discussion around trying to improve dry run and making even more realistic and handle more situations that currently dry run cannot handle. Keeping up with those changes and making them super easy to use. There could be a time when you could do 90% of your smart contract testing in the dry run mode. I think you'll always need to test on a private network, on a test run. I would never tell you don't do that. You should always do that, but there could be a time where you could get most of your confidence already purely in dry run in a very easy to do manner and very quickly. And that's kind of like where I'd like Graviton to be at and make possible. So I think just but dry run itself has to improve, and I think it will. I hope it will.
Just wanted to mention another analogy that I think about when I first stumbled upon Graviton, and I'm not a big expert on Reach, but if I understand it correctly, they also have some sort of pre-built formal verification methods for the test. So when I first time seen the Graviton available and looked into the documentation, it seemed like an analogy of that capability in Reach, but an analogy that is perfectly suited for projects that rely on pure PyTEAL and PyTest, essentially. This is that missing link for people who were, I suppose, PyTEAL purists and were wondering if Algorand is working on something like that. And the answer is yes. As you can see, Graviton is essentially there to address that particular niche. All right, Zeph. So I'm sure there is a lot of topics that we can continue discussing on Graviton, and I'm actually thinking that we could perhaps do a little checkpoint some many months from now to see after Graviton will also add some of the things that you've just mentioned in regards to the roadmap. From my side, I hope that this episode is going to help a bit with the adoption, because I feel like adoption at some point is going to become a very important factor as well. So that there would be feedback coming from the users, and you would be able to reflect on the analytics and how people in the ecosystem are relying on Graviton and etc. But as I did with the episode 1, I'm just really curious to ask this question to you on, and this is off topic from Graviton, but what advice would you give for software engineers who want to try their hands on blockchain development or on Algorand, or just generally get into Web3 space? And I asked this to Cosimo in episode 1, and I figured it will be very interesting to keep asking this from different guests to see their different takes on it. So I would love to hear your take on it, essentially.
So I think, as always, it really depends where you are in the process, but there is a brand new entry point on our developer portal for absolute beginners. But even if you're not an absolute beginner, I think if you're a beginner to Algorand, I recommend you go through them. These are the so-called Algorand Challenges, and they're a nice way to learn by doing. Currently, there are only 4 challenges, but they're already covering some of the main ideas and differentiators for Algorand, and you get some cool NFT badges as part of the process. So the first exercise is on payment transactions. So you'll actually have a challenge to create a payment transaction, either in Python or JavaScript. Then ASA creation. So ASAs are the native tokens that you can be created on the Algorand blockchain that either represent tokens or NFTs. Smart contract creation and deployment is one of the challenges, and atomic transactions, another differentiator of the Algorand blockchain, which makes it a very inherently secure way to send transactions to the blockchain. So even if you're a seasoned smart contract developer, I urge you to try those. And once you have that under your belt, there are many other directions you could go. I suppose if you're a smart contract developer, you'll want to figure out how you want to interact with the blockchain. And I think that's an easier decision. Basically, you're going to typically choose the language that you're comfortable with. So we support natively 4 languages, Python, Go, JavaScript, and Java. But there's other community-driven SDKs as well, and C# and others as well. So that's kind of easy. So that decision point is pretty easy. Like, yeah, choose the language you're comfortable with and learn the SDK. But how do you actually write the smart contracts, that's a little harder decision. You can do it for very simple programs. You can write them directly in TEAL, but we talked about this. I think it's getting less and less tenable for complex programs, given the complexity of the AVM now, to write them in pure TEAL. But yeah, some people can do that. By all means, go ahead. But I think for most people, probably want to choose a higher level language like PyTEAL or Reach. And maybe in the future we'll have other really well supported options as well. But I don't want to speculate too much about that. But I believe there'll be other options as well. Yeah.
I see. Yeah. Thanks for the advice, and with that, Zeph, thank you for joining this episode. I think we covered a lot of very interesting topics. I personally learned a lot of extra information about Graviton, especially on the influences, and it's really amazing to see how you managed to also leverage some of your experience in different domains of computer science as an inspiration for the project. And so with that, I hope you're going to enjoy listening for episode number 2. And unfortunately, I cannot name the guests for the episode 3 so far, but they will be announced accordingly on the AwesomeAlgo channel. Thank you very much for listening, and Zeph, once again, thanks for joining and being a guest today.